Representing numbers in binary is fundamental to understanding computer science, and in this video we'll be exploring how it works, how you can convert between decimal and binary number systems, and some basic binary operations. As we covered in our last video, binary is a base 2 numbering system, which means that it only uses two digits, 0 and 1. So how do we represent numbers larger than 1? Well, to understand this, let's have a look at how humans count normally. Humans normally count in denary, where we use only 10 digits, the numbers 0 to 9, to make up all of our other numbers. When we want to represent a number larger than 9, we simply add another digit in front of the previous number. So, to represent the number 13, we put a 1 in front of the 3, which means that we have 1 10 and 3 1s. We know the positions of these digits by increasing the powers of 10 that we use, with the rightmost digit representing 10 to the power of 0, the next digit representing 10 to the power of 1, the next 10 to the power of 2, and so on. We can do the same with binary, where each digit represents a power of 2, because binary is a base 2 number system. This means that the rightmost digit represents 2 to the power of 0, which is 1, the next 2 to the power of 1, which is 2, the next one 2 to the power of 2, which is 4, and so on. So in this example, we have 1 4, 0 2s, and 1 1. If we add these up, we get to 5, meaning that 1 0 1 in binary is 5 in denary. We call the bit with the largest value, which is the bit on the left-hand side, the most significant bit, and the bit with the least value, which is on the right, the least significant bit. For your exam, you'll need to be able to convert 8-bit, otherwise known as 1 byte, binary numbers into denary. So let's have a look at an example on how to do that now. If we were asked to convert the binary number 100111011 into denary, we start by drawing a table with 8 columns and filling in the binary numbers right to left, where the rightmost digit is 2 to the power of 0, which is 1, the next is 2 to the power of 1, which is 2, the one after that is 2 to the power of 2, which is 4, and so on until you get to 2 to the power of 7, which is 128. We then fill in the binary number we're looking to calculate. So in this case, we have a 1 under the 128 column, a 0 under the 64 and 32 columns, a 1 under the 16 and 8 columns, a 0 under the column 4, and a 1 under the 2 and 1 column. Next, we multiply each binary bit number with the denary number that it represents. So in this case, we multiply 1 by 128, 0 by 64, 0 by 32, and so on until we have calculated all of the values in the row. We then add up these multiplied values, which gives us a value of 155. That means that 1001111 in denary is 155. We also need to understand how to convert denary numbers back into binary for our exam. There are multiple ways that you can do this, but in this video we're going to focus on the table method, which I think is the most simple. To do this, like with our conversion from binary to denary, we start by drawing a table with 8 columns and filling in the binary numbers from right to left, where the rightmost digit is 2 to the power of 0, which is 1, the next is 2 to the power of 1, which is 2, the next is 2 to the power of 2, which is 4, and so on until you get to 2 to the power of 7, which is 128. We then start at the left-hand side of the table and try to subtract our denary number from each of the values. So, in this case, we try to subtract 128 from 163, which is 35. As 35 is a bigger number than 0, we put a 1 underneath the 128 column and carry on with the remaining 35. We're now under the 64 column, so we subtract 64 from 35, which gives us minus 29. As minus 29 is less than 0, we put a 0 under the 64 column and keep carrying the 35 forward. We're now under the column 32, so we subtract 32 from 35, which gives us 3. As 3 is bigger than 0, we put a 1 under the 32 and carry the 3 forward. We're now under the 16 column. We subtract 16 from 3, which gives us minus 13. Minus 13 is less than 0, so we put a 0 under the 16 column and carry the 3 forward. We're now under the 8 column, so we subtract 8 from 3, which gives us minus 5. Minus 5 is less than 0, So we put a 0 under the 8 column and carry the 3 forward. Likewise, as we're under the 4 column, we subtract 4 from 3, which gives us -1. As -1 is less than 0, we put a 0 under the 4 column and carry the 3 forward. We now get to the 2 column, so we subtract 2 from 3, which gives us 1. As 1 is bigger than 0, we put a 1 under the 2 column and carry the 1 forward. We're now on the final column, which is a 1, so we subtract 1 from 1, which gives us 0, so we put a 1 under the final column. As we've now reached 0, we're done. If we had any more columns on the right-hand side, we'd simply put a 0 in the rest of them, but given that we're at the end of this table, we don't have to worry. So now we can pull all of these numbers out of the table so that we get a binary value of 101000011, which is 163 in binary. You'll also need to know how to add two binary numbers together for your exam. Luckily, this is quite simple as long as you remember the following 4 rules. Rule 1 is that if you add 2 zeros, you get 0, just like you do when we add numbers normally. Rule 2 should also be pretty similar, as this is when you add 0 and 1, you get 1. When you add 2 ones in denary, you get 2, which isn't possible in binary. So instead, you carry a 1 to make 1 0 in binary. Rule 4 is when you add 3 ones together. Then you get a 1 and you carry a 1, so you'll get the binary 1 1. Let's see these rules in action with an example. Let's calculate 100111110 plus 00010011. First of all, let's plot these values onto a table with 2 extra rows, one for our carry values and one for our final sum. We'll start off in the far right of the table and add the 0 and 1 together. As we can see from rule 1, 0 plus 1 is 1. So we write 1 in the answer part of our table and carry 0. We then move on to the second to last column, where we add 1 and 1. According to rule 3, this gives us 0 with a carry of 1, so we plot this in the table. Next, we need to sum 1, 0 and our carry of 1. So again we use rule 3, which gives us 0 and a carry of 1. We have the exact same operation in the next cell as well, adding 1, 0 and 1 together, which again gives us an answer of 0 with a carry of 1. The next column gives us a sum of 1 plus 1 plus 1, which according to rule 4 is 1 with a carry of 1, so we plot this in the table. We then need to sum 0 plus 0 plus the carry of 1, which according to rule 2 is 1, so we put this in the table with a carry of 0. We then sum 0 plus 0 plus 0, which according to rule 1 is 0, so we plot this on the table before doing our final sum of 1 plus 0, which is 1. Therefore, the binary addition of 100111110 plus 000100011 is equal to 10110001. If you've got time in the exam, I'd always recommend converting these 3 numbers back to denary to check that you've got the right answer. In this case, the question's asking us to calculate 158 plus 19. We've got an answer of 177, which is what 158 plus 19 equals, so we know we've done it all correctly. If we take a look at another example where I've changed the second value's most significant bit to be a 1 instead of a 0, making our addition in denary be 158 plus 147, this should equal 305. However, if we look at the table below and calculate the denary value of our result, we've got a value of 177, which isn't 305. Why is that? Well, this has been caused by what's called an overflow error, which is where the value we're trying to store has exceeded the maximum value that we can store. In this example, we've only got 8 bits of data to play with, which means the maximum value that we can store is 2 to the power of 8 minus 1, which is 255. 305 is larger than 255, so therefore we've got an overflow error. We can see this in our calculation. If we look at the addition of our most significant bits, the bits on the left, we can see that we're summing 1 plus 1, which according to rule 3 is 0 with a carry of 1. However, because we've not got an additional bit to store this carry value on the left, the result of the calculation is incorrect. You'll also need to know how to left and right shift binary numbers for your exam. Performing a binary shift simply means moving all of the bits in a binary number to the left or right. Binary shifting to the left multiplies a number by 2, whereas binary shifting to the right divides a number by 2. If we take the example of performing a single left binary shift to the number 0010010, which is 34 in denary, then we start with the least significant bit and move its value to the next bit up. We then do the same for the next bit, which is a 1 in this case, and move it up by 1 bit. We keep doing this until we reach the most significant bit, which we remove from the number. We then add a 0 to the least significant bit column and we're done. If we convert this number back to denary, we'll see that the value is 68, which is double our starting value of 34. Likewise, if we want to right shift this same binary number, we take the most significant bit and move it down 1 bit. We keep doing this for all of the other bits in the number before discarding the least significant bit's number and adding a 0 as the most significant bit. As we can see, the right shifted binary number here is 00010001, which is 17, and half of our starting number of 34. So, there we have it. In this video, we've covered what the binary and denary number systems are and how to convert between them. We've also looked at how you can perform binary addition as well as binary right and left shifts. So that's the end of this video. If you'd like to test your knowledge and access other lesson resources, then make sure to head on over to revisio.uk.